This video is made in terms of the International Program on Machine Learning conducted by Peking University. My name is Alexander Gruzdev. I am a postgraduate student from Irkutsk, Russia. Aviation has experienced a tremendous performance since the 12th century. For more than 100 years, we learned not only how to fly, but how to break the sound barrier, how to climb 11,000 meters and more high, and what's more important, we were able to do that not only impressively, but effectively. But you know what? The question is, really, are we? What does it mean, effectively? In this presentation, I'll introduce the base of the optimal control theory. We discuss the main techniques and traditional problems that may and have to be solved in aircraft dynamics, consider the traditional algorithm to do so, and even discuss state-of-the-art machine learning approaches. So of course, first of all, I would like to start from a theory. I would like to start from scratch and provide you with a term of optimal control. We know that optimal control theory is a branch of mathematical optimization that deals with finding an optimal control for a dynamical system over a period of time such that an objective function is optimized. Mathematically speaking, as far as you can see, the optimal control problem may be formulated as a minimization of a certain function and finding such a control input that would minimize that function over a certain period of time. So the weather got worse, unfortunately, and we had to change the location. First of all, let's make as smooth an introduction into the domain as possible. All the methods of solving optimal control problems may be divided into two huge groups: traditional methods to do so, and method that involves artificial intelligence as the most powerful tool right now. As for the term optimal control, it was first introduced by the Russian mathematician Lev Patnyagin in the 1950s. It was like 70 years ago. In spite of this fact, there are a lot of methods and algorithms that were developed by talented mathematicians, scientists, and engineers all over the world. As for traditional methods, that may be divided into two main groups that names respectively open loop control and closed loop control. And let's start from the first one. So, open loop control. It's one of the simplest and most basic forms of control systems. It involves using a predetermined set of control inputs or actions to achieve a desired output, without considering the system response or feedback. There are many open loop controls, such as an on-off switching of valves, machinery, lights, motors or heaters, where the control result is known to be approximately sufficient under normal condition without the need for feedback. One of the main advantages of open loop control is simplicity and low cost. Since it does not require sensors or feedback mechanism, it can be implemented using relatively few components and, what's more important, with minimum programming effort. However, it also has significant limitations, since it cannot adapt to changing conditions or unexpected disturbances in the system. As a result, it's often used in combination with other types of control systems, such as closed loop, we will discuss it later, or adaptive control, to achieve more robust and flexible performance. Well, now let's talk about closed loop control. It's a method of controlling a system by using feedback to adjust the input based on the output. The goal is to maintain a desired set point or target value despite disturbances or changes in the system. Its name comes from the information path in the system. Process inputs have an effect on the process outputs, which is measured with sensors or processed by the controller, it doesn't really matter. The result, the control signal, is fed back as input to the process, closing the loop. So now I think it's pretty understandable that the basic idea behind closed loop control is to continuously monitor the output of a system and adjust the input to maintain the desired set point. This is achieved by measuring the output, comparing it to the set point, and then adjusting the input based on the difference between the two. By doing this, the system can respond to disturbances or changes in the system and maintain the desired output. Closed loop control is way more popular in mechanical systems because it's easy enough to implement, it's robust enough, and isn't required to overperform the system. By saying that, I mean we usually do have sensors in responsible system, and it makes the implementation way more easier. So now let's consider the exact example. The most popular solution, according to my experience right now, is to use a PID controller to control the system. PID stands for Proportional Integral Derivative Controller, and the distinguished feature of such a controller is the ability to use these three control terms to apply accurate and optimal control. The block diagram shows the principles of how these terms are generated and applied. It may also be described by this formula. To demonstrate the performance of such a controller, I'd like to use an example from MATLAB simulating. Here we have a system that dynamics is described in this block. We use a PID controller to achieve the desired water level. In this formulation, by the way, the PI controller, without the derivative component, works way much better, and it reveals one of the main cons of such controllers. You have to find the optimal values of coefficients for them to perform well. Despite this fact, PID controllers are really robust and useful even in flight dynamics. They may be and actually are used to control simple systems in non-complex conditions. For instance, in the task my former flight dynamic teacher and I are solving right now, the PID controller I use to maintain the desired speed of the aircraft. Well, I suppose now it makes way more sense to you, and we may outline advantages and disadvantages of traditional algorithms. I would like to start from mathematical rigor. Non-neural network algorithms are often based on well-established mathematical principles and can be proven to converge to an optimal solution. As for the second one, it's of course their computational efficiency. Many non-neural network algorithms can solve optimization problems much faster than neural network-based approaches. And the third one is interpretability. The output of non-neural network algorithms is often easier to understand and interpret than the output of black box models like neural networks. But of course, nothing is ideal, and traditional algorithms probably have their own disadvantages. The first disadvantage I would like to outline is their limited flexibility. Non-neural network algorithms are typically designed for specific types of optimization problems and may not generalize well to other types of problems. Obviously, they have also difficulty in handling complex systems. Some non-neural network algorithms struggle to handle large complex systems with many variables and constraints. The third one is the sensitivity to initial conditions. Some non-neural network algorithms can be sensitive to the initial conditions and may need careful tuning to achieve good performance. Yet another disadvantage I would like to outline is the lack of adaptability. Non-neural network algorithms are generally less adaptable than neural network models and may require significant modifications to handle changes in the system. So traditional methods obviously may provide you with a good solution, or at least with suitable enough. Unfortunately, the development of the system we use makes us worry about optimal control more and more. The more complex and complicated a system is, the more inputs and outputs it has, and the more complicated and uncertain its dynamic is, the more errors occur during control and the more difficult it is to create the optimal policy. The idea of using artificial intelligence methods, such as deep neural networks, seems rather obvious, isn't it? But it's not as simple and obvious how to exactly use it. We've got used to the use of neural network in classification and recommendation systems for estimating, predicting something. But what about optimizing and creating the most optimal policy? What about this context? The idea behind using neural networks and artificial intelligence in optimal control is to improve the performance of controllers by leveraging the power of machine learning algorithms. Optimal control, as we've already discussed it, is used to find the best control actions for a system that minimize a given cost function subject to dynamic constraints. Traditionally, optimal control methods rely on mathematical models of the system dynamics, which can be complex and computationally intensive. Neural networks, on the other hand, are powerful function approximators that can learn to map inputs to outputs without explicitly modeling the system dynamics. This makes them well suited for solving optimal control problems because they can learn to generate control actions that optimize the cost function based on system data. By combining neural networks with optimal control, we can develop more flexible and robust controllers that can adapt to changing environments and handle non-linearities in the system dynamics and so on. All the methods that use artificial intelligence, I would like to divide into two large domains, those that use reinforcement learning and those that don't. Let's start from reinforcement learning. It's a type of machine learning where an agent learns to make decisions by receiving feedback in the form of rewards or punishments. The agent takes action in an environment and receives a reward based on the outcome of those actions. Through trial and error, the agent learns to take actions that maximize the total reward it receives over the time. In other words, reinforcement learning involves an agent making decisions within a given environment while aiming to maximize the cumulative reward it receives. The agent's actions are guided by a reward signal, which is provided by the environment in response to the agent's behavior. By continually adjusting its decision-making process based on the feedback it receives, the agent can learn to make more and more optimal decisions over time. This makes reinforcement learning particularly useful in scenarios where there is no clear-cut solution, but rather a range of possible actions that can lead to various outcomes. So the question is, why do you want to use reinforcement learning to solve optimal control? First of all, it's their flexibility. Reinforcement learning can be applied to a wide range of problems, including robotics, gameplay, and autonomous driving. The second one is because reinforcement learning provides you with the possibility to learn from experience. Agents learn by interacting with their environment and receiving feedback in the form of rewards or penalties, and that allows them to improve over time. And probably in some scenarios, this formulation of the task may be more suitable than the other ones. The third one is connected with decision making. Agent can make decisions in complex and dynamic environment where traditional rule-based systems may not be feasible. But the most fascinating feature that reinforcement learning provides you with is the ability to explore the environment. Agent can explore new strategies and options which can lead to discovering new solutions or approaches that weren't planned in the basic formulation of the task. But of course, some problems may occur. First of all is because reinforcement learning agents require a lot of data before they can learn effective policies, and it makes the training process slow and computationally expensive. The second problem you may face is instability. Reinforcement learning algorithms can be unstable and difficult to train due to the large search space or non-convexity of the optimization problem. Reinforcement learning agents may also have difficulties with generalizing to new situations outside of their training environment, leading to poor performance in novel scenarios. And finally, the most difficult and the most painful part is reward engineering. The design of an appropriate reward function for an agent is a challenging problem. It requires domain expertise and careful consideration because you always want to avoid unintended consequences or undesirable behavior. Well, now as for supervised learning. We know that supervised learning is a type of machine learning approach in which the algorithm learns from labeled data, and supervised-based optimal control is a method used in control theory to optimize the performance of a system, logically. The goal of this approach, again, is to design a control policy that minimizes a specified cost function. One of the key features of supervised-based optimal control is that it requires a priori knowledge of the dynamics of the system being controlled. That means that the controller must have access to a model of the system, which describes how the system evolves over time in response to various inputs. Well, unfortunately, I haven't managed to use this approach myself yet, but in the literature I've read, there are several exact methods that can be used to solve optimal control problem within the framework of supervised learning. If you are interested in this topic, you probably gotta read this reference and this one as well. I've told you about the task my former flight dynamic teacher and I are solving a bit earlier, and now I'm ready to explain what exactly we are going to achieve. The task is to train a reinforcement learning agent to fly the plane at an extremely low altitude. In this case, there is only 1 meter between the surface and the plane. So, this problem is crucial not only because such a maneuver is rather dangerous and even tiny uncertainty in the system may lead to a catastrophe, but also because the lift force of the plane near the surface of the Earth is higher because of the ground effect. We are pursuing to train a TD-free agent. You can read about this actor-critic model here. In this block, we have a dynamic of the aircraft. Now, all the parameters except the angle of the rudder is controlled by PID controllers. It's our environment. Our agent is here in this block. It gains all the observations as the vector, the reward, and make actions as follows. Action here is the angle of the rudder. This block contains a reference trajectory agent has to teach to use. In this block, we have a reward function. As I said, it's the most difficult part. As an inspiration, we use a task formulation from this article, and I strongly recommend reading it. We haven't achieved good enough performance yet, but I believe we would be able to do so as soon as possible. Well, of course, there is still a lot to be desired. Hardly ever could I fit all the material and all the knowledge about the domain in one 15-minute presentation. To sum up, I'd like to leave here the references I used for the preparation, and also to express gratitude to all the people that have been involved in the course. I really appreciate that Peking University provided me with a unique opportunity to get more familiar with such an interesting research direction. Thank you for watching.